On the first day of November 1955, the United States Atoms for Peace exhibition opened in Hibiya Park, Tokyo. America's ambassador to Japan, John M. Allison, conveyed a message from President Eisenhower that the exhibit stands as a symbol of our country's mutual determination that the great power of the atom shall be dedicated to the arts of peace. Matsutaro Shiriki, now chairman of Japan's Atomic Energy Commission, termed the exhibit an historic curtain raiser on the atomic age in Japan. A message from Prime Minister Haruyama, read by Chief Cabinet Secretary Nomoto, praised the greatness of atomic science in the present century and welcomed the exhibit as an educational movement. Visitors came early that first day. The long line gave evidence of strong interest in how the atom provides power for peace. Then the climactic moment. And the first of what 6 weeks later would be, 1/3 of a million persons started moving through the big doors. It was an exhibit holding promise for the future, yet there was a past to be considered, a realization that what was taught by Democritus 2,000 years ago was pertinent to today. He claimed all the world was made of atoms, too small to be seen, that in size, the atom is to the apple as the apple is to the world. In 1896, Henri Becquerel learned certain elements are unstable, that their atoms are constantly changing in form, giving off rays of energy. Working with Becquerel, Madame Curie discovered that chief among these unstable elements is radium, which emits extremely powerful rays. The atomic fuel uranium contains some radium. It was Ernest Rutherford who discovered the atomic nucleus, the core of the atom, source of its energy and most of its weight. And Niels Bohr provided the theory of atomic structure, revealing the atom as a miniature solar system with electrons for planets, the nucleus, its sun. Later, theoretical physicist Hideki Yukawa of Japan provided new facts about forces in the atom's nucleus with his meson prediction theory. In 1930, Ernest O. Lawrence invented the cyclotron, a device which smashes atoms so that scientists can learn more about their structure and energy properties. It was Albert Einstein who revealed through his theory on the nature of relativity that mass can be transformed into energy. And Otto Hahn in 1938 was first to split the nucleus of the uranium atom, which resulted in the release of tremendous amounts of energy. The process was called nuclear fission. Enrico Fermi conceived, then built an apparatus of graphite blocks which could sustain the nuclear fission process as a chain reaction. He called it an atomic pile, where the fission process could be induced, sustained, and controlled. Man finally could claim a degree of control over the power of the atom. You will see now by what means and in what fields the atom's power is at work for peace. This is a full-scale model of the graphite reactor at the Brookhaven National Research Laboratory, used mainly for the production of radioisotopes. The graphite moderates the speed of the neutrons. The fuel rods are inserted into the reactor. The fuel is a rod of uranium. Bombarded by the neutrons inside the reactor, most elements become radioactive. Elements artificially made radioactive in this way are called radioisotopes. At the side of the reactor, materials which are to be made radioactive are inserted inside. A control rod governs the reactor. Made of a neutron-absorbing material, the rod, while it is inside the reactor, prevents the chain reaction. When the rod is withdrawn, the fission process commences. The green bars represent the uranium. The black is the graphite. With the rod withdrawn, neutrons are left free to fly, free to strike and to split uranium atoms. The splitting of one uranium atom leads to the splitting of nearby uranium atoms in geometric progression until the whole of the uranium is reacting, producing great heat and high radiation, always controlled and contained by the reactor. Inserting the control rod halts the reaction. Materials inserted earlier, having been bombarded by uranium neutrons, are now radioactive. They require careful handling. Scintillation counters, Geiger counters, measure degree of radioactivity. A special pipetting device can transfer radioactive fluids. The technician is protected by special glass and lead bricks. When exposed to a radioactive source, a Geiger counter makes a clicking sound. This sound diminishes when lead bricks are placed in between. The lead bricks absorb radiation. Another handling device, magic hands, the operator protected by a transparent shield and distance. She may even manipulate materials without seeing them directly through closed-circuit television. These radioactive materials, called radioisotopes, have a variety of uses, all of them important, many of them unusual, most of them quite simple. In medicine, for example, radiation from radiocobalt in this therapy machine can be used to destroy cancerous tissue. Its capacity is that of a 2 million volt X-ray machine, which would cost 3 times as much as this apparatus. Radioactive iodine taken in solution collects in the thyroid gland to reveal thyroid activity and treat disorders. radioactive phosphorus applied to birthmarks can, with consecutive treatment, remove such marks. Atomic reactors designed specifically for medical purposes are under construction. The atom's power is essential to modern medical science. In industrial fields, the atom has won a reputation as the factory's most efficient inspector. A radioisotope automatically checks package levels. Longer-wearing tires are made possible by checking tire wear through radioactivity. In the textile industry, mixing of colored dyes is regulated by a radioisotope. Thickness of sheets of metal or plastic or paper is kept constant by an unerring radioactive monitor. In the petroleum industry, a radioisotope can prevent the uneconomical mixing of petroleum products. Use of the atom today in American industry is saving an estimated 36 billion yen per year. The atom's power is as appropriate to the farm as to the factory. By using radioactive materials, agricultural scientists are able to learn how plants make food, how man can help plants produce more food, by discovering which fertilizer plants use most efficiently, by exposing plants to radiation to produce cell changes which could result in stronger crops. In animal research, radioactive tracers provide new knowledge, for example, about egg production. Knowledge which is translated into less breakage and more food. The improvement of plant species by means of irradiation has produced higher yields. For example, a new type of peanut plant has a 30% higher yield. The world is only just beginning to tap the resources of the atom. To know more of its potential, scientists have amazing devices for experiment and study. This is the CP5 heavy water reactor, cut away to show how the uranium fuel rods are arranged in the heavy water. The heavy water in this type research reactor serves as moderator instead of graphite. Here, the fission process may be utilized in a variety of ways to discover new atomic energy possibilities. Another type reactor called the swimming pool. Fuel rods are simply suspended in distilled water. The fission process can make materials inserted at the side radioactive. The CP5 and swimming pool reactors used for research and training aid in the development of reactors to produce electric power. These newest power reactor designs are achieving 3 dimensions through actual construction in the United States. Completion is expected before 1960. From these designs, researchers hope to discover the techniques best suited to the production of electricity. Fissioning uranium, turning water to steam. The steam forced through turbines, which activate generators, producing electricity, providing cities and towns with light and heat at a fraction of the consumption of conventional fuels. Another type power reactor, prefabricated and transportable by air. could supply electricity to remote areas where fuel transportation is especially expensive. This is the future, in which there are those who see atomic-powered trains hauling great distances, fueled by less than a cubic inch of fissionable material, and great ships which could stay at sea for years without refueling. An exciting new profile on the high seas. Or atomic-powered planes that swiftly girdle the globe, linking peoples and nations. This, then, is the Atoms for Peace exhibition, where we have seen evidences and designs of the past and present, which give promise of a richer, fuller tomorrow. A future not bound in the hands of fate, but in ours.